Everyone to our final full day of the Gauge Sage Community Science Workshop. I'm Beth Pratt-Sutola, the project manager from UNAVCO for this, and I am very pleased to introduce our Greg and Margaret, who are the plenary chairs for our final plenary session, New Approaches to Processing Big Geophysical and Geospatial Datasets. All right, thank you.
All right, thanks, Beth. So good morning, at least California time, and welcome to plenary session 3A of the Sage Gauge Community Science Workshop. My name is Greg Burrows. I'm from Stanford University, and together with Margaret Darrow from the University of Alaska, I will be chairing this, the first of two sessions today on new approaches to processing big geophysical and geospatial data sets. So the motivation behind these sessions is that the size of geophysical data sets that are enabled by new sensor technologies holds great promise, but also presents profound challenges for how we do our work. So as the velocity, the volume, and the variety of data available increases, that enables a higher spatial and temporal resolution of the sort of processes we're trying to understand, which is fantastic. However, that comes with a parallel increase in the demands on the community in terms of data acquisition, in terms of data compilation and data management, and in terms of data analysis, visualization, and even distribution. So today's session showcases different aspects of this, different ways, strategies for meeting these challenges, and in doing so, to realize the full potential of these new data sets to develop the sort of insights that we want to develop into how the Earth behaves, which of course is the goal. So this effort will require new technical approaches such as scientific machine learning, benchmark data sets, open source approaches, and even new modes of data access and data processing such as cloud and edge computing. So with that, let me turn things over to Margaret to introduce the first of this morning's speakers.
Great, thank you, Greg. Yes, today our first speaker is Michael Bianco. He's an assistant scientist at the Scripps Institution of Oceanography at the University of California, San Diego. And his presentation today is called Machine Learning in Seismology and Acoustics, Tomography and Beyond. So here's to Michael.
Hi, my name is Mike Bianco, and I'm a project scientist at the Scripps Institution of Oceanography, studying ML in the context of earth science. And today I'll present some recent work of ours in machine learning and model selection in seismic tomography. This is work performed in collaboration with my colleagues at UCSD and at San Diego State University. This is Peter Gerstoft, our student Zhang Zhu in the ECE department of UCSD, and Kim Olson in the Department of Geological Sciences. I'd also like to thank the organizers of SAGE and GAGE, this workshop, for organizing this and inviting me to give this overview talk. I'm going to focus on tomography with seismic noise. And so for those of you who are unfamiliar with noise tomography, so seismic events are relatively rare, but ocean atmospheric interaction, for example, ocean waves that correlate with the bottom of the ocean, or that is continuous. And so this interaction provides near continuous excitation of the solid Earth. And it turns out that we can use this noise signal, this what used to be considered nuisance, to perform tomography. And the way this is done is actually by correlating the travel times between different stations, different seismic stations. And then when you do that, you actually can get a correlation peak that corresponds to a time delay between the two. And from what we know about the basic equation for velocity, so distance equals speed times time. And then so slowness is just 1 over the speed. And so using sort of the inverse of speed allows us to formulate a linear measurement model. So here we have our data, which are travel times, and we have the different paths between the different stations as this matrix A, our tomography matrix. And then we try to actually estimate based on many different cross correlations between all different combinations of different seismic stations an image. And so this is a discrete image, in this case, n pixels. And essentially what we want to do is, given these measurements, given our assumptions about the propagation and some noise on the signal, we want to estimate this model. And so here's an example of a model obtained using the Southern California Seismic Network. And this is a low velocity region corresponds to the Los Angeles Basin. And this, for instance, a higher velocity region corresponds to the Sierra mountain range. And so what I'll show today is some of our results using machine learning to build on this sort of basic measurement model and obtain high resolution images of subsurface structure. And so this is one data set I'll discuss in this talk, which are sort of dense measurements from the 7x10 kilometer array that was installed in Long Beach in 2011. And here's their subsurface image that we obtained with our machine learning approach. And just as an overview, I'll first kind of take a step back and introduce more basic machine learning concepts. And then I'll discuss our work in seismic tomography and the relevant applications. And also discuss the importance of generalization and model selection. So when you're performing machine learning or any sort of statistical analysis, the model that you obtain, ideally should generalize well to unseen observations, and that's sort of the stick by which all models should be measured. And so in machine learning, often interested in training a model that produces desired output given inputs. And so in supervised learning, we actually have, a label for each example. In unsupervised learning, we have no labels. And the goal here is to find interesting properties of X. As I'll show, the inputs here contain structure that can be either manipulated for a later supervised learning task or just for trying to visualize and understand structure in the data. The approach I'll discuss a little bit actually combines these two methods. So we actually have travel time labels, but we actually have no real a priori data set for the geophysical structure we'll try to learn. And this is learned in an unsupervised way. So either given simply the data, you want to reproduce the data, learn something interesting about it, or you want to be able to reproduce these labels, such as this image of a cat or a dog. What kind of seismic wave is this? Is this a P wave? Is this an S wave? And we want to do this, we want to train the model. And so the idea in machine learning is that, essentially what we want to do is start out with a highly complex model and use it to tell us what the useful features of the data should be versus the other way around. And it's been found in many fields, image processing, language processing, earth science, that often these learned representations work much better than sort of what we can hand engineer ourselves. And the point is being that these features are essentially updated based on our desired task, right? So in this case, with the neural network, the features can be updated with backpropagation to be optimal for a given task. And so here I have a simple example with neural network classification of the MNIST data set. And I'm sure a lot of you had seen this data set before, but it's just an illustrative example here. Is we have 784 inputs for each image and a single output. What this label is it all 0? Is it a 3? Or is it a 9? And this is just a simple 2-layer network where we have 2 layers of weights between the single hidden unit. And we can see that if we train this network, which is a very simple network, which attains about 90% accuracy on this data set, we visualize these weights, we can actually see they correspond to little pieces or fragments of digits. For instance, looks like a number 5 if you squint. And so taking a look at unsupervised learning, so for instance, clustering in 2D, we can see that it can be useful for discovering this hidden structure in the data, right? And so we can start out initializing these clusters to being, some sort of arbitrary location, and then iteratively refine them to find these points using simple nearest neighbors updates. But actually, similarly, the same thing can be done for very high dimensional data. So in the case of dictionary learning, for instance, we can take patches of these images. In this case, we'd have about 10,000 patches for this image. We can actually see that a subset, of this data, a few hundred of these sort of centroid patches, right? These represent roughly all the variation we would expect to see. So each one of these represents sort of a cluster in very high dimensional space. And so we'll apply this, in this case, 64 dimensional space. So we'll apply this to seismic tomography here coming up. But we can see that in general, these lunar representations are very interesting and useful for these particular kinds of problems. So now moving on with applying this to seismic tomography, we can assume that we have some slowness map, and we have basically two different models. And we call this approach locally sparse tomography, because at large scales, we use a simple least squares constraint on the travel time measurements and regularization on the slowness model, which induces some smoothness. But we also have this local sparse model, which says that little patches of the seismic image should have a sparse representation under this dictionary. And not only do we represent them sparsely, but we also try to learn this dictionary from the data. So as I showed you before, we have this discrete tomographic image that we're trying to obtain, travel time measurements from different combinations of stations. And so we can see then that this overall slowness model is governed by the travel times. And then this next layer at the local level, we use these travel times then to learn a dictionary. And so again, the stations here are on red and the rays are in blue. And this approach is actually developed in one of our papers from 2018 called Travel Time Tomography with Adaptive Dictionaries. And it has a lot of other examples that I won't be able to address here. But here's an example of this LST, locally sparse tomography approach in action. So we have basically a checkerboard velocity pattern here, in this case slowness, which remember is just 1 over velocity. And we have 64 stations and kind of a Gaussian distribution here. And what we do is we get all the ray paths from all these stations. You can see in the middle, the sampling is very dense, but on the outside is not so dense. And what happens is we initialize the system to have uniform velocity, and we initialize the dictionary to be noise. And so what happens is we get this initial global slowness model. The dictionary learning then is able to exploit the structure that is in this model to then update this image. And we iteratively refine both models, ultimately this being our final slowness model, and this being the dictionary that we learn of all the patches that represent this seismic structure. And so we can see that, after a few iterations, this converges to almost the exact Oracle image, right? So this is granted a fairly simple scenario. We wouldn't expect to see checkerboard, travel time or checkerboard slowness patterns, in a true seismic scenario. But this gives us some way to interpret, what the system might be able to learn in a geophysical scenario, right? So it turns out these little patches, correspond exactly to the structure that we're trying to learn here in this checkerboard image. We can see that it converges very well to, this horizontal slice with the true slowness and the estimated slowness here. And so now we'll talk about, again, this application of this approach to this Long Beach data set. So in March 2011, there were about 5,200 seismic stations deployed in Long Beach over about a 70 square kilometer area. And ambient seismic noise was cross-correlated for all these unique virtual source receiver pairs. And you can imagine all the unique combinations of these individual receivers as very, very large. And so this gives us about 14 million ray paths from this 3 weeks of data. And just considering only the 1 hertz vertical component allows us to look at Rayleigh surface waves, which are essentially like ocean waves propagating across the surface. They're seismic waves that travel on the surface of the solid Earth. And we can see that the image that we obtain is really interesting. It actually is able to show us this area of very high velocity that actually looked like an anomaly at first until we took a look at sort of borehole records here. And it turns out that we believe what we're seeing is actually the extent of this Silverado aquifer. And so we believe the study can help characterize aquifers in this region. And so we look forward to seeing what other results come out from this. So now I've shown you an application of our approach, but now I'll start talking about how important it is to think about, in this case, model generalization. And so in general, in any sort of modeling approach, you want to obtain good model generalization, meaning that you want a system that is able to predict labels or values from inputs that were not seen during training, right? So ideally, you've had enough data to train the model that well represents your data, and then your model is the correct model to represent this data to be able to predict values that weren't seen, right? And so we can think about selecting model complexity in the parameters for any given model for many different models by evaluating the performance on a test set. And so we can see here, back to this example of linear regression, we actually have is a curve that's actually generated by a sinusoid, right? And we're trying to fit it with different polynomial degrees. And we actually add a little noise here too. We can see that as we increase the degree of the polynomial, the polynomial is actually able to fit the data exactly. And so we can actually take a look and see what happens on data that was withheld from training, right? So we actually got 0 error on the training set in this case. But if we continue to draw more samples from this data, we can see that by increasing the polynomial degree, the errors actually diverge, right? So when you actually fit the data exactly, your error explodes, right? Because you're not actually really learning a predictive distribution of the data, you're just memorizing the training data, so to speak. One sort of straightforward approach for doing this that we talk about in our paper, recent paper that's submitted based on Ridgecrest data, is that we use this cross-validation approach, right? So in this case, model, as I mentioned, model complexity and parameters is selected by evaluating performance on a test set. So what we can do is actually take, for instance, our data, divide it in this case into several chunks, right? And save one for test and use the rest for train. And we do this multiple times without replacement. So here's some results from seismic tomography from this Ridgecrest study that we just submitted. And here is the error surface of the travel time residual from the IRIS 3J network in Ridgecrest. And so here are the error residuals for our locally sparse tomography model. So we can see that we have, for instance, these 2 parameters here in addition to a few others, but for visualization's sake, we can just look at 2. We can see that, in general, what we want to do is try to obtain a minimum travel time residual on the test set, given our training data. And so, this kind of takes us back to a kind of philosophy that we're trying to develop here, where that in seismic tomography, in the case of travel time tomography, the input features are travel times. We believe that the best velocity model then should best predict travel time measurements from a region, right? And so what we're going to do then is choose our model based on minimum travel time residual on the test data. We use seismic data that was recorded between July and September of 2019 from the IRIS 3J network in Ridgecrest, California. And this is a location of where a lot of earthquakes happened in that period of time. And in this data, there were 342 nodes in total. There were about 65 evenly distributed nodes and 277 dense arrays near the fault strands in the Ridgecrest area. And then we performed noise correlation. So we ignored the large events and used only the sort of continuous ocean atmospheric interaction to perform our tomography. And then we inverted for the geophysical structure in the region at several surface wave frequency bands using our locally sparse tomography approach and a conventional least squares inversion. And we compared how well the models can generalize to the data. So one point in this data set, and we think this is relevant to many other data sets, is that the ray coverage in the inversion was very irregular, right? So we have this, sort of a discrete image that we're going to impose on this ray coverage, but we have all these sort of unevenly distributed rays, sensors and rays, corresponding rays. And what we do is we actually normalize the travel times, the sampling from the travel times in our reconstruction to be uniform. So we apply a weighting function to our travel time residuals such that our resampling in our inverse problem results in a uniform distribution of rays. And so here's our tomographic image of the Ridgecrest region, and we can see that this low velocity regions correspond very well with radar satellite imagery of the damage zones in this area. This is our 1 Hertz phase velocity image and gives us about the top 1 kilometer of the ridgecrest area. So sort of the average velocities over that, that area. And so we perform cross-validation on the data set. And what we do is we resample the data into tenfolds, sort of following this uneven azimuthal distribution to avoid bias in our cross-validation approach, meaning that, you know, say there's few ray directions that dominate the travel time data that we don't repeatedly select from here when we're doing our resampling, that each time we draw evenly from all these directions. And so what we do in this case, this example of one of the folds from our tenfold cross-validation is that we you know, train on these 10 chunks from each azimuth bin, and then we test on the remaining chunk. It means repeat this process 10 times and average the results. Here's our results for doing the cross-validation procedure on least squares for these different frequency bands for the Rayleigh wave surface waves, and then doing LST and sort of our analysis of the differences of the approach. And so again, these are obtained using Rayleigh wave group travel times. These are actually average images from all of the cross-validations. We actually can see is that LST predicts lower velocities in the low velocity zones than LSQ overall, with a little more contrast along the edges. And so here's an example. We can see these 2 kilometer per second contour lines here in our velocity images. And we can see that these differences correlate again with, you know, the physical, the other physical ground truth information that we have about this region. Another thing that this allows us to do, this resampling approach, cross-validation, is that we can get uncertainty in the data. Essentially, you know, doing tenfold cross-validation gives us 10 different models. So not only do we have the average, but we also have, you know, standard deviation of the models, right? So we can see the uncertainty or the confidence of the models. You can say overall that LST is more confident about its estimate. But what we can see then is also that the travel time residuals from least squares overall by the minimum cross-validation error from least squares are greater than LST for a couple different cases, RAM initialized, least squares initialized. And so, so we can see that the LST model, given our current experiment, that it generalizes better to the travel time measurements. Effectively, you know, we conclude that providing sort of a better velocity model because it generalizes well to. And so using cross-validation, we're able to show this, that, you know, this is relevant to any sort of more data-driven approach. And so overall, you know, not only can it be used for model selection, but it can be used for comparing models, right? And so I'll just leave with that. And I'll just say that I think there's many interesting opportunities for machine learning research and applications in seismology. I've just presented one approach to tomography here, in machine learning called locally sparse tomography. And you know, you just want to be careful in applying any model to data. It's important to understand how well it generalizes, because that's actually its true value. And you know, we're arguing here that the best tomography models are the models that best explain the travel times, and we try to demonstrate that in a principled way. And cross-validation is one path forward for quantifying generalization and model uncertainty in ML generally. So thank you again for your time. And if you would like to find this LST code, the code again is available on GitHub, and these are some references from this talk. Thank you.
Hey, Greg, you're muted.
Rookie mistake. Yeah. So thanks, Michael. And that was a great talk. And so Michael's available. I think we have 5 minutes to take questions. So maybe we start. I see there's one from Victor Sai in the chat. Victor, do you want to unmute yourself and ask that question, or would you prefer that I ask it?
Why don't you go ahead and read it if it's there?
Okay, so
and then we'll just leave the raise hand action, you know, for anyone who wants to say something verbally they haven't typed.
Okay, so Victor asks, how different and/or consistent are your results from other studies like Lin et al. 2013 or Bowden et al. 2015 using the same data set? Are there clear differences that are thought to be improvements on the previous images?
Are we talking specifically about iconal tomography then?
Well, there have been several tomographic studies with that same data set. And so interesting question is, how is yours different, and can you assess which one's more closer?
Sure, yeah, well, I think that they actually both contribute to the model. So I think that the LIN data follows a very physically principled approach to estimating geophysical structure from or at least travel time measurements, except one problem potentially with iconal tomography is that it doesn't actually minimize the travel time residual. So it may have actually trouble representing larger scale features because what's happening is you're actually taking a gradient of a travel time surface from each virtual source, which can introduce noise into the measurements. And so I would say that in the LIN study, for instance, it's really interesting in that they also have model uncertainty and everything else. But I think because of some of the noise introduced by differentiation, is that you actually get, so you can't really capture as well as we have larger scale features. And so I would say that what we have here is sort of able to model well, larger scale features and maybe better the boundaries that delineate certain features also.
Okay, thanks for that. So Manu Shirzai asks about the thoughts about including physical constraints for maybe prior knowledge of geology or geodesy into your approach.
Yeah, I think that's very would be a great thing to do. That's definitely something we're taking a look at doing, is actually incorporating some sort of domain knowledge into the machine learning method. One naive way might be to just incorporate this, sort of pre-train a dictionary on existing, sort of maps to get some initial geophysical dictionary of structure. But yeah, I think there's a lot of ways to go forward with that for sure. One thing we're beginning to look at in training neural networks is actually incorporating, in the case of room acoustics, incorporating physical models into the training, and so that you essentially start with some initial guess of what the right answer should be based on physical knowledge. And this is really helpful in the case where you have unlabeled data, so machine learning relies on labels. And if you have a lot of unlabeled examples, you can at least use, sort of a first principles approach to get a rough estimate of what your model should be, and then refine that, with training data if that's available.
Okay, so we should probably move on after this one brief question. So Robert Casey asks, how do you best qualify the arrangement of stations that prevent oversampling at certain azimuths?
I think it depends on sort of the average source direction. I think one thing we were just trying to prevent happening is just, there's sort of like biases, right, depending on the source direction. So if you have, for instance, ray directions that are perpendicular to the, average, sort of source direction, for instance, this being the ocean for noise tomography, then you can have, very high velocities, right? And so that's something that should also be considered. We were just trying to avoid introducing some biases by oversampling parts of the specific geology of the area.
Okay, thanks. So with that, I think we need to transition to the next speaker, Margaret.
Michael,
okay,
thank you very much. Thank you very much for your
Thank
presentation
you.
and the great
Absolutely.
questions.
And thank you for having me.
So our next speaker is Lindsay Hagee, and she is an assistant professor at the University of British Columbia. And her presentation today is community-driven development of open source tools for geophysical inversions. So we'll get started with her presentation.
Hello, everyone. Thanks for taking time to join me today. I'm pleased to be a part of the Gage Sage Community Science Workshop and to have the opportunity to share with you some of the work that we're doing in the SIMPEG project to collaboratively develop tools for simulations and inversions in geophysics. I'm an assistant professor at the University of British Columbia, and I work on computational methods, including inversions and machine learning with geophysical data. I contribute to SIMPEG, which we'll be talking about today, as well as geosci.xyz, which is a project where we're working on developing open educational resources in the geosciences. So as motivation for this talk, I've got an image here that's it's a collection of applications where we need to characterize the subsurface. So this might be for resource exploration, if we need access to minerals or groundwater, for geotechnical applications, so assessing if a slope is stable or if ground is stable to build something infrastructure like a dam, as well as for energy and our interactions with the subsurface as we work to mitigate climate change. So finding geothermal energy resources, locating areas where we can capture and store CO2. In all of these applications, we need to be able to characterize the geology and the subsurface in 3 dimensions. So how do we do this? Well, we can use direct sampling. And so by this, I mean, we would drill a hole, and this gives us a point measurement of local geology. And so we can characterize that one location. But if we need to characterize larger areas, and ideally doing so non-invasively, geophysics has an important role to play. So a basic geophysical experiment, we've got some sort of source that's going to input energy into the subsurface. And this can be a controlled source, or it can be a natural source, for example, Earth's magnetic field. And then we're going to measure data that depend on the physical properties of the subsurface. So for example, if we make gravity measurements, these are sensitive to density. If we make measurements of the magnetic field, these are sensitive to magnetic susceptibility. I do a lot of work in electrical and electromagnetic methods. So for example, here we've got an image of a DC resistivity experiment. And so in this experiment, we inject current into the subsurface, and currents are going to flow and charges build up depending on the electrical resistivity of the subsurface, as well as chargeability. And this is the ability of a rock to act like a capacitor. That then impacts the voltages that we measure on the surface of the Earth. We could also look at an electromagnetic experiment. So here I've got an image of a magnetotelluric experiment. And so in this experiment, we use natural EM fields, EM being electromagnetics, energy from the solar wind, from lightning strikes worldwide. These generate EM energy. Impinges, plane waves impinge on the subsurface of the Earth. And where currents flow and the response of electric and magnetic fields is going to depend on actually all of the properties in Maxwell's equations, but primarily electrical resistivity. And so the electric and magnetic field measurements that we make on the surface of the Earth are sensitive to these subsurface properties. And so what are some of the things that we need to actually work with these data and work with these experiments? Well, there's 2 types of problems that we need to be able to solve. So we'll start with the forward problem. And so what this is if we've got a model of the subsurface of the Earth, we've got a model of the subsurface physical properties, we want to go ahead and solve some sort of partial differential equation to simulate what the data should be. This is a well-posed problem. So given a model, we can predict what the data are. Going the other way, if we have measurements of geophysical data on the surface of the Earth, we then want to actually estimate a physical property model of the subsurface. And this is what's called the inverse problem. And the inverse problem is ill-posed, which means there are many potential physical property models of the subsurface that are consistent with our data. And so this is where it becomes important to be able to impose assumptions and bring in different data sets. For example, if we've got petrophysical information or geologic information about the setting that we're working in. And so to solve both of these problems, we need computational tools. And so let's just take a look at what's kind of the list of some of the things that we need. So we need to be able to describe our model of the subsurface of the Earth, define a survey geometry, and solve a partial differential equation to simulate data. And then going the other way, we need to be able to construct an optimization problem and bring in these assumptions or other information that we might have about the geologic setting that we're working in. And so SIMPEG is an open source project where we've been working on developing tools for simulation and inversions for a range of geophysical data types. So I've got a list here on the left of the geophysical experiments that are currently supported in SIMPEG. So we've got potential fields, we have gravity and magnetics, electrical and electromagnetic methods, both in the frequency and the time domain, and both of those support controlled and natural sources, as well as fluid flow. And so let's take a look at SIMPEG. How do you actually use SIMPEG to solve some of these problems? So let's start by considering the forward problem. So we want to be able to discretize the Earth, assign physical properties, and solve a partial differential equation. So the first step of that is we need to discretize the Earth. And so we're going to create a mesh. So SIMPEG is written in Python. So the code that you're seeing here is Python code. And so in these 4 lines, what we're doing, the first 2, we define the widths of the cells in each direction. And then in the 3rd line there, we create a mesh object. And so being an object, and Python being an object-oriented programming language, we've got this mesh object, and it then has properties and methods that we can work with. So for example, once we've defined the geometry, we also know where the location of all of the nodes and the centers. These are properties of the mesh. We also have methods like this plot grid method, where we're able to actually go ahead and plot up and visualize our mesh. So this shows you a 2D mesh. There's a range of mesh types that are supported in SIMPEG. So we've got 3D tensor, cylindrical meshes. We've also got octree meshes. And so Joe Capriotti, I've included his image here. He deserves a lot of credit for the current octree implementation in SIMPEG. And where these meshes are quite powerful is they're adaptive meshes that let you reduce the number of cells, and that reduces the computational cost. So as we're scaling up to really large problems, this is a really important advancement in the SIMPEG project. Okay, so we've got our mesh. Now we want to go ahead and actually solve a partial differential equation. So here I've got one example. We've got the DC resistivity equation, which is a classic div sigma grad phi Poisson equation. So on the top, we've got the continuous version, and then beneath that, we have the discrete version. So here we're using finite volume methods to discretize the differential operators. So again, you can see that each of these differential operators are properties of the mesh. Once we know the geometry, we can access these differential operators. And so we can go ahead and assemble our system matrix and solve that to be able to predict where the currents are and what our data should look like. And so, earlier I showed you the list of methods that are currently supported in SIMPEG. But SIMPEG and many projects that are open source and within the Python ecosystem, are modular toolboxes. And so if you've got a PDE that you want to solve that needs some of these tools, but isn't necessarily implemented, you can use these components to build up and go ahead and solve whatever partial differential equation you're working with. So this gives us the forward problem. Let's take a quick look at what we need for the inverse problem. So the way we set up the inverse problem in SIMPEG is as an optimization problem, where we form an objective function that consists of 2 parts. So the first part being the data misfit. So this is basically a measure of how well do our predicted data represent the observed data. And the predicted data are again coming from a forward simulation where we've got a model and we're going to solve that PDE to see what the predicted data should be. But as we've mentioned, the inverse problem is ill-posed, and so we also need to impose some regularization. And so these can be things like simple assumptions, like asking for a smooth model. But this is also a space where you can bring in additional data types. So if we know something about the petrophysics of different rock units that we expect to see in our area, this is something that we can try and bring in through the regularization. So we combine these 2 terms with a trade-off parameter between them, and then we can go ahead and solve this optimization problem. And so with that, I want to show you a bit of a sampling of some of the problems and active research being done with SIMPEG. So on the left here, we've got an example of magnetic inversions. And so this work is being led by Dominique Fournier. And he's been working with remnant magnetization and working with inverting for remnant magnetization in 3 dimensions. And so there's 2 things to consider when you're working with magnetic data. There's an induced component, and this comes from the Earth's magnetic field interacting with rocks that have a magnetic susceptibility, have substantial magnetic susceptibility. There's an induced component. That's the same as if you basically pick up a paperclip with a magnet, you induce a magnetization into that paperclip. But the magnet itself, it has a remnant magnetization, and rock units can have this as well, where it's basically a permanent magnetization that's frozen in when magma comes out and cools. That magnetization direction is going to be basically frozen in the same way that the Earth's magnetic field is pointing at that location. And so what's really exciting about this is this can, when we're inverting and getting 3D models of magnetization, can start to be a tool for understanding tectonics, because we know perhaps a given rock unit had a magnetization direction that we maybe expect to be the same if a unit was in place around the same time. And if we start to see variation in that, maybe that gives us some indication of folding and faulting. On the right, I've got an example of research by Soggy Kang. So he's been doing work looking at airborne electromagnetics over the Central Valley of California. And so managing aquifers and managing groundwater is a critical problem in the Central Valley right now. And electromagnetics is sensitive to electrical resistivity, as we've mentioned, and so can provide indications and be used to characterize sand units versus clay units. And this can be really important for understanding where aquifers are and also potentially connectivity between different aquifer units. A couple other examples. On the left, we've got work being led by Thibaut Astic. He's looking at joint inversion methods that are combining data sets that are sensitive to different physical properties. So for example, gravity is sensitive to density and magnetics are sensitive to magnetic susceptibility. And so how do we combine two distinct data types with distinct physical properties? Well, we can do so by looking at petrophysical relationships as one example. And so Thibaut's been looking at bringing in petrophysical and geologic information into the inversion to build up quasi-geologic models of the subsurface. One other example that's currently under active development that I wanted to highlight because of connections with this community is 3D magnetotellurics. So solving Maxwell's equations on large scale with natural sources. And so some of the motivation for really pushing on this implementation within SIMPEG is some of these exciting data sets being collected on very large scales. So for example, AusLAMP in Australia or EarthScope in the US. So this gives you a bit of a sampling of, some of the data types that we're working with, some of the problems that can be solved. And so, SIMPEG as a tool can solve these types of problems. But I want to take a step back and, ask the question, well, what is SIMPEG? And so, yes, SIMPEG is an open source project and open source software toolbox that you can use to work with these data sets. But it's developed by a community, developed by people and folks who are in industry, folks who are in the academic space, but have in common that we want to be working with geophysical data and solving this suite of problems. And so it really is kind of a multi-stakeholder project where we've got contributors from a number of different institutions and backgrounds. And so, this really highlights, I think, that SIMPEG as a project is, yes, it's code, it's tools, but it's also community. And so having practices that enable collaboration is a really critical component of development. And so being able to have practices for collaborative development of software. So some of the standard things you hear about like versioning, issue tracking, testing, being able to go through a pull request review, which is basically peer review of suggested changes, are all important components of being able to collaborate on a project. But additionally, communication practices are really important. We're people, we're working with each other. And so having weekly meetings, and we record each of those. So if folks can't make 1 week or just want to keep a pulse on what's going on and not necessarily show up to the meeting, all of those are available. We also have places for communication, such as forums, as well as chat. And so I think, SIMPEG is perhaps one example and of, a community and toolbox interest that's useful and interested in solving some of these challenging problems in the earth sciences. And I think what's so important when we think about the problems that we're really facing and some of these really important problems that are impacting society is that they're multidisciplinary. Geophysics is one component of any of these problems of locating and managing groundwater. Geophysics gives us the electrical resistivity of the subsurface, but we need to couple that with hydrology, with geologic knowledge, and with stakeholders who are actually managing aquifers in order to make positive progress. And these types of problems are challenging. Each domain can have different terminologies. You know, the way we use the words model and data can be very confusing between different domains. Each person from a different domain comes with different conceptual building blocks. So having tools to be able to communicate ideas and share data and methods across different domains is really important. And I think that, you know, open source software and educational resources have a pretty critical role to play in facilitating multidisciplinary research. And so one final example that I want to walk through that has used the SIMPEG project, and where sort of SIMPEG has been a bit of a, one of the building blocks, is a project that we've undertaken with Geoscientists Without Borders. And so in this project, we were working with folks in Myanmar, and the goal is to build up capacity for local engineers and geoscientists to locate aquifers using DC resistivity. So we're working in an area called Mon State, and for several months of the year, surface water resources dry up. And so it becomes really important to be able to access groundwater. And so there's a few components to this project: building local capacity, so being able to train folks to go out and collect data, invert those data, and identify potential drilling locations. Providing tools, so we actually brought, the folks who went to Myanmar. So Sagi and myself were support crew from afar, but Doug, Ren, Max, and Devin went to Myanmar, brought some DC resistivity equipment, and worked with folks for a couple of weeks to do training, both out in the field and with open source software to be able to work with those data. And so, you know, being able to actually have SIMPEG code, you know, up and running, and being able to have folks be able to train locals to be able to use that was an important component of that. And it's more than just, you know, providing the code. You know, providing lines of Python is useful, but it's not necessarily useful if folks are not familiar with software development, and that's not something that they should have to do in order to be able to work with these data. And so this is where, you know, working in a broader open source ecosystem is really important, and being able to leverage tools like Jupyter Notebooks to create interactive widgets and interactive interfaces for folks to be able to explore the physical equations and to work with the data that they have collected. And so I think this is a nice example of a project that, you know, yes, includes some of the geophysics, the tools that we use in our own research, but also reaches out to a very societally important problem. And that there are tools that we can rely on. You know, we can bring some of our cutting edge research tools and make those accessible by using tools in the open source ecosystem, like Jupyter. And the way that we have collected a lot of these resources is through the geosci.xyz project. So collected interactive notebooks that you can play with to explore how geophysics is used and might be useful in a given problem. But also to provide background information. So background on inversions, background on the DC resistivity experiment. And, you know, this is important for training and education. But I think, you know, as we go towards and are looking to solve some of these multidisciplinary problems, it really blurs the lines between who's a student and who's a researcher. We need to be learning from each other in each other's domains. And so education, I think, in educational resources is a critical component of that. And so we've talked a fair bit about SIMPEG, but as I mentioned for the groundwater project in Myanmar, you know, SIMPEG being a part of an open source ecosystem is a really important component. And so what that kind of means when I talk about an ecosystem is we're building upon, contributing to, and benefiting in advances from tools that are in this broader Python landscape. So for example, Jupyter for interactive computing, Dask for running computations in parallel. You know, there's a blossoming ecosystem and suite of tools in machine learning. And so by bringing all of these tools together, each one has its own focus in its domain, but is interoperable with the others, lets us build out and continue to benefit from advancements in each. And I wanted to focus and give a bit of indication too about the use of Jupyter, as this is such an important component for being able to run interactive computations, both for building up, your own research workflows, but also for creating interactive widgets and creating tools that allow people to explore equations. Is that, yes, this is something that can run on your own machine, but being able to access Jupyter Hub really lets this scale, which is quite exciting. So Jupyter Hub lets Jupyter be installed for multiple users on cloud infrastructure and on HPC infrastructure. And so this is a really important, step forward to be able to really reduce the barrier to accessing high performance computation and large scale computation, is that the same notebook that runs on your laptop can be scaled up to run at an HPC center. And another project to mention is the Pangeo project, and this is another community in the open source Python space, and it's a project that's really been bringing together and investing efforts and time and energy into some core tools for large-scale geoscience research. So as I mentioned, Jupyter for interactive computing. Other projects include Dask, X-Ray, and Czar for being able to really scale up computations. And I've included a couple links here to resources that let you explore some of the implications of projects in Pangeo. So there's the gallery that's got a suite of examples, and then the Jupyter Meets the Earth project is developing resources to onboard folks and kind of give a bit of a tour of what's in the Jupyter ecosystem. So if Jupyter is new to you, I'd encourage you to check those out. All right, so as we wrap up, we've started in geophysics and branched out a bit into the broader Python ecosystem. And coming back to, again, some of these problems that we're looking at in this suite of challenges, I've got a sampling of in these images below. These are challenging problems that are multidisciplinary, that intersect with society. And I think, open source projects have a really important role to play. These challenges are bigger than any one individual. And by working in an open source way, you can build on the work of others. You can enable others to build on your work. These having interoperable tools lets us bridge across disciplinary lines. Having open educational resources provides some tools for learning how to communicate with different disciplines. And so with that, I will say thank you very much. Thanks for your time. Here's a few resources to reach out and get in contact if you're interested. And again, here's the link for the slides. Thanks so much.
Thank you, Lindsay. So you've done a good job of answering questions in the chat, but there of course are more. Manu asked about about what it says could, but I think it means cloud. And I think you probably addressed that in a subsequent slide after his chat, because there were clear references to cloud computing. Is that correct?
Yes, so one of the great things, and just briefly mentioned this in the chat, but happy to expand on it. One of the great things about working sort of in the open Python ecosystem and really focusing on the software is you can deploy that code in multiple places. So SimPeg can be deployed on your local machine or on an HPC or cloud facility. And tools like Dask are really key for making that possible, because Dask lets you actually abstract away how you parallelize code. And so you can basically write your software using Dask to parallelize SimPeg, and then give instructions for whatever machine you're on. But we don't actually have to change much under the hood within SimPeg to make that work.
Great, thanks. And so Jonathan McCarthy sort of asked about navigating the balance. If you could give some sort of personal remarks about how you've managed to do this as an early career scientist.
Yes, it's certainly a challenge, and definitely, I think, something that as a community we need to work on. Is giving credit for folks who are developing software, because it is a lot of work. But I think one of the things that we've tried to maintain within SimPeg is a bit of this tension and balance of working on new problems, working on research, and then taking a moment to refactor what you've done so somebody else can extend that and use it. And one of the things that we've noticed, there's this initial sort of, I think, you have to really get a project started and get it to a critical point before you can really start to do sort of new things and combine things. But one of the things that I think has been so exciting to see is that by developing it in a modular way, you can actually then start to exchange ideas across different sort of subdomains in geophysics pretty rapidly, which I think ends up allowing us to sort of accelerate the pace of research. So one quick example I'll give is Dom Fournier implemented methods to do sparse regularization. And he was focused on magnetics, but because it's in this modular framework, we can immediately use that in electromagnetics. And that opens up sort of, new opportunities that just wouldn't be possible if we were working sort of each in our own silos.
Okay, great. Do we still have time, Beth? Can we keep going?
I think we're going to have to call it for this session. So thank you very much for the chairs and for both of the speakers. This same plenary session will continue with 3 more speakers in the last session block of the day, which starts at 5 p.m. Eastern time. In the meantime, before then, the next hour, the other half of this session block is e-lightning posters, those flash poster sessions with about half a dozen mini presentations in them. So we'll transition to that in the next couple minutes. And then the middle block of the day, we're coming back to the special interest group sessions. We did have a last minute cancellation, so there are 3 there instead of 4 as originally planned, because somebody's up in Alaska dealing with the response for the field there. And so if there doesn't happen to be a special interest group session that appeals to you, I urge you to maybe consider messaging and setting up a meeting with somebody you would like to collaborate with at this meeting. Okay, we're going to end this session now, and we'll see you over in the posters.